So now we're going to get into matrices and what are matrices, how can we use them, and then we're going to start talking about Gaussian elimination and Gauss-Jordan elimination. So when we talk about a matrix, it's just an easy way to organize data. And in this case, our data is going to be a system of equations. So when we talk about a matrix, we usually use these square brackets to do matrices. And we're going to have numeric entries here, and these are going to be row numbers. It's going to look like this. That first row is A11, A12, A13, all the way to A1N. Second row, A21. Notice that that first number is telling you what row it is, and the second number is telling you the column that it's in. So this is entry A22. This is A23 because it's in the second row, third column. And this is going to be A2N because this is in the nth column, but second row. So third row would look like this, A31. 3 is telling you the row number. The 1 is telling you what column it's in. So A32, A33 to A3N. And then we could have as many rows as we needed. I'm going to make this just a little bit bigger. We can have a M1. So now we are in the mth row. A M2. A M3. Because that's in the third column. All the way to a MN. So we're talking about row number. This guy is row 1. Rows go horizontally. This is row 2. Row 3, and then row M. And then we're talking about columns. I'm going to abbreviate COL for columns. So column 1, write it that way. Column 2, column 3, and then column N. There. Columns go up and down. Think about like columns of a building. They go up and down as well. So a matrix is really made up of a whole bunch of different entries, and each one of these denotes an entry here. And generically, we can write that as Aij. I is going to be the row that it's in, so the row number. J is equal to the column number. So, once again, just to kind of emphasize that, because this is the language we're going to use for the rest of the semester. Everything we do this semester is going to be based around matrices. If we're talking about, let's do this entry here, then A23 means that this is the item that lives in this matrix, and it lives in row 2 and in column 3. So if we look at row 2 and column 3, there that guy is right there. So you can tell where it lives based on those little subscripts there, the 2, 3, or even like 2N, second row, nth column, and so on. Now when we identify the size of a matrix, it's always going to be the number of rows by the number of columns. So in this case, we have M rows and we have N columns. So this is an M by N matrix. So just for fun, let's go through and let's identify a few. Suppose we have a matrix that looks like this. And we want to know what is the size of that matrix. Well, this matrix has 2 rows. And it's got 3 columns. 1, 2, 3. So this is a 2 by 3 matrix. Now we could identify any entry in any point in there. Suppose we want the entry that is in A23. Well, we are looking for the one that is in the second row. And it's in the third column. So the second row is here, the third column is here, that entry is 4. So Now, number 4 is in the A23 slot of the matrix. Let's do another one. And if you want to, you can always pause the video and you can look through this and determine what kind of matrix we have. How big the matrix is. So if we look at this one, we have 1, 2, 3 rows. And we have 1, 2, 3, 4 columns. So this is a 3x4 matrix. And just for fun, if you remember vectors back in 171, they were sometimes written this way. A vector is really just a special case of a matrix. And we could identify the dimensions of this matrix. This has 1 column and it's got 1, 2, 3 rows. So number of rows by the number of columns means this is a 3x1. And suppose we had something like that. We know this is a matrix because of the brackets there. It has 1 column, it has 1 row. Number of rows by number of columns means this is a 1x1 matrix. Now, matrices are a nice condensed way to write a system of equations. So let's say we have a system of equations. Maybe we have this system. So we have x minus y plus 4z is equal to 12. 2x plus y minus z is equal to 3. Negative 4x minus 5y plus 7z is equal to 9. So there's our system of equations. Let's write this a little bit more condensed way. So we can write what's called an augmented matrix. And the augmented matrix is really just a nice, quick way to write this. And you can think about it this way. All the coefficients of x will go in 1 column. All the coefficients of y will go in a column. All the coefficients of z will go in a column. And then we have a place where the equals kind of divides this. And then we're going to have the numbers that's on the other side of the equals. So here's how we do this. Each equation is really just going to be represented by a line in this matrix. Now, when you write an augmented matrix, it's important that it's in the proper form before you try to put it into the matrix. So notice that I've got the x's, y's, and z's all on the left side, and we have numbers on the other side. So that's your proper form. Notice also I've got my x's lined up, my y's lined up, and my z's lined up. It just makes it easy to kind of pop those numbers into that matrix. So if we look at that first one, we have a 1x, we have a negative 1y, a 4z, and we said that's equal to 12. We have 2x, a 1y, a minus 1z is equal to 3, a negative 4x, negative 5y, 7z is equal to 9. So there's our augmented matrix. It is just a nice condensed way to really write a system of equations, or that's one of the purposes for matrices. Let's do another one. This one's going to be a little bit more interesting. I'm just going to kind of jumble some things up here. So let's say we have a system that kind of looks like this. Well, this is not in proper form. We really need to try to rewrite this and reorder this and make this just a little bit easier to deal with. So to be in proper form, we need all of the variables on the left and we need the plain old numbers on the right. So if I were to rewrite this, that first equation has that criteria. X's, Y's, Z's on the left, variables on the left, numbers on the right. But I'm going to reorder everything because I need to really line up those X's, Y's, and Z's. So I'm going to rewrite that as X minus Y minus Z is equal to 12. And that second equation. Notice we have X and number stuff on the right. So I need to move that X term to the other side. So to do that, I'm going to add 4X to both sides. So we have a 4X and then we have a positive Z. So put plus Z there is equal to 5. So we're just kind of reordering everything using those rules of algebra, moving terms to the other side as necessary. And then that last equation. Right now it says 9x minus 4y is equal to 2 minus z. So once again on the right, we don't have the number by itself. We need to move that z over, and we can do that by adding z. So we have 9x minus 4y plus z is equal to 2. So when I rewrite the system, this is in proper form. Notice the x's are lined up vertically, the y's are lined up vertically, and the z's are lined up vertically. And then we have that equal separating the variable terms from the number terms. So if I want to write the augmented matrix here, so that first equation says 1x minus y, so put minus 1 there, minus z is equal to 12. I have 4x. Now, notice there's no y here. It's understood to be a 0y. Because remember, 0 times anything is still 0. And then we have a 1z is equal to 5. And then we have 9x minus 4y plus 1z is equal to 2. So there's our augmented matrix. I do like to draw this line in. This is an imaginary line. It would not show up on a calculator or anything like that. But it's just to kind of let me know that, hey, this was a system of equations to begin with, and that's where the equals would have been. Now, if we want to identify the matrix dimensions, we got to identify how many rows and how many columns we have. So we have 1, 2, 3 rows, and we have 1, 2, 3, 4 columns. So this guy's a 3 by 4. The one up here was also a 3 by 4 matrix. 3 rows, 4 columns. Now, if we can take a system of equations and we can put it into an augmented matrix, we can also take the system out of the matrix. And it works the same way. Remember that first column represents x coefficients, second column represents y coefficients, and that z column represents, that third column rather, represents z coefficients. So if we were to take this out of augmented form, this would say x minus y minus z is equal to 12. And that is that first equation. The second line says 4x plus 0y plus z is equal to 5. And that is that second equation. And then 9x minus 4y plus z is equal to 2 is that third equation. So we can go into augmented form and we can come out of augmented form. Let's look at another one. Suppose we have a system that's in this form. And this is a system of equations. So notice we have 2 rows and we have 1, 2, 3 columns. So this is a 2 by 3 matrix. So our variables could be x and y. Or we could say x1, x2. So what are the equations that are produced from the system? Well, we have a 2x, and we're going to have a 1y. This is where the equals is, so that's going to be equal to 3. And then we're going to have a 2x plus 5y, and that's going to be equal to 7. So there's the system produced by that matrix. We could think about this one in the same concept, same way. And these are two different examples. Let me label. So 2 rows, 3 columns means this is a 2 by 3. So that top row, I'm going to call these X and Y. So we're going to have 1X plus 3Y is equal to 4. And this is going to be 0x plus y is equal to 2. So there's our basics about matrices. How can we identify dimension, and how can we go into augmented form and take a system and pull it out of augmented form. In the next video, we're going to talk more about row operations and some special forms of matrices called reduced row echelon form and row echelon form.